It should be. Okay, it's live. Okay, it's live. Okay. Okay, so it's working. Hi guys. Welcome back to the stream for RAG. So building RAG in Pure C. It's been a while since I've streamed last time. So we're back again with another stream session. So thank. Okay, yeah, let's start. Okay. The thing that we left off last week was um, this, right? So I'll just show you the devlog, right? So the last week, what we did, last 2 weeks, perhaps, right? So what we did was we worked on version 1. So version 1 is the flat binary file. What we did was not the generation part, but we did the storage and retrieval. The generation is left. Generation from the LLM is still left. Okay, still left. Um, so, but we did the storage and retrieval. So storage is the flat binary file on disk. So we're uh, basically writing all of it to the file, the text, the embeddings to the file, and then brute force linear scan with cosine similarity. That's what we did. This is in respect to the backend, which is storing the embeddings somewhere. Okay, so um, that's where this is, right? So this the versions, right? The versions is in respect to the backend, which is storing and embedding somewhere, right? So version 1 is that. So version 1 is the flat binary file that we're doing. Generation with the LLM is still left. And then should write this API to main.c, that's fine. Finish the backend. Yeah, finish the retrieval for version 1, which includes public API to write the store to a binary file, among other things. Topcore query. Topcore query we also did, and then write and free also this API we did. If you want to see the API, or if you want to see the main.c, so we can just go through over what we did. So first this is all includes chunk.h. So chunk.h is the our implementation for chunking. So it basically takes in input text. So the query, so you can write something like so this chunk text takes an input query, user, or a file. So it's a user query. So let's focus on user query, right? So let's focus on user query for now, and input query as text, right? And overlap is the chunk overlap between two chunks, right? Between two chunks. So it's modeled like this. So if, for example, um, there's a text like this, right? uh, okay, so this like okay, this is the input query, for example. Now the chunks is actually divided into so it's like, for example, the chunk size, for example the chunk size can do chunk size is equal to 4, and overlap is equal to 2. Okay, which means that the chunk size is right. So okay, 1 second, this is a mistake here. Okay, no, that's fine. The first chunk will be like this: ABCD chunk 1, right? And chunk 2, okay, chunk 2 will be CDEF, right? And then this will be GH, right? So this is chunk 3. Okay, so these are chunks, and the overlap, you can see there are two characters of overlap between two chunks. That's the overlap that we're talking about in this. So generally, how, I mean, it matters because the overlap matters because the amount of data that's there in between two chunks, the more the overlap, the more semantic meaning will be there between two chunks. So it's responsible for not losing data, not losing information between two chunks, right? So we can the other chunk can also, the second chunk can also have good information, a good amount of information, so such that the cosine similarity score will increase for the second chunk also, if that makes sense. So overlap is useful for not losing chunk information between two chunks, and the number of chunks is just for convenience. So the number of chunks and chunk size, all of these um, are tweakable, right? And chunk free just takes in this API returns the array of chunks, right? Okay, and takes in the array of chunks and returns word. Okay, fine, that's fine. But what it does internally is just mallocs it, right? Mallocs the chunk idea, right? Yeah, we're just freeing it. So here we're just freeing it. So you will see the yeah, let's see the implementation here. So yeah, as I said, so if the text is not there, so if the text is is 0, then text is null, you return null. And if the chunk size is 0, chunk size cannot be 0, so we return null again to standard error. And if the overlap is greater than chunk size, so it's streaming. Okay, cool. If the overlap is greater than chunk size, then again it reroutes to standard error, and text length is equal to str length text. Okay, that's fine. Step is equal to, so okay, now text length is we use the string library, string library here to get this function strlen. So okay, that's cool. So step is chunk size minus overlap. Chunk size again we get in from the function parameter, and step is basically, now what is step actually? So step is the it's just an internal metric used by memcpy, as we can see later, which basically represents the start of next chunk. Okay, so it just makes it easier. It's just a convenience, just a convenience variable, if you will. Okay, and the count is text line minus overlap by step, right, plus 1. The count is used here, right? So um, how many times you should call mem memcpy or malloc? Yeah, malloc. Are we calling memcpy? Yeah, we are calling memcpy later on, but yeah, malloc is just allocating the array from the heap. Okay, that's fine. And then we are basically copying the text plus start. The start is the variable uh, which is represents the start of the chunk, and each chunk is separated by step amount, right? Step amount of units, and it's just convenience variable allocate array of chunk pointers. And then this is the okay, this are just allocating the array of chunk pointers. That's cool. And this is just yeah, this is just error checking. That's fine. And then length is equal to chunk size. That's fine. And then if start plus length is greater than text length is equal to text length minus start. So if the start plus length is greater than text length, right, which means that which means if you are at the last chunk, and the length of the chunk is not needed, right, the whole amount of chunk size is not needed for the last chunk. For example, the chunk size is 5, right? The chunk size is 5, and text length to the last is just, for example, it's just um, yeah, where yeah, how can I explain it? So chunk size is 5, right? So ABCD, for example, and start plus length, we are done that. Okay, now this is greater than text length, which means we're overflowing the actual text, right? We're overflowing the index of the actual text. Then actually the length of the chunk should only be text length minus the start. That makes sense because we're not blindly allocating the chunk size to the last few number of characters for of the last part of the original text. We're just cutting the chunk size down to what is actually required. That's all. So that is this. So that's fine. And then allocate an array of chunk pointers here, and then we are allocating each chunk. So each chunk at this amount, the size of length plus 1, right? And plus 1 is for the delimiter operation, right, that we're doing here, right? That's cool. So that's what we're doing here. But yeah, we're taking each and every array element, and we're allocating the size of that element, right, of that array element into, again, an array of length plus 1, right? And then this is failed, then we just free what we already allocated, free chunks of j. Okay, j goes from j to IE. So whatever we have allocated, we free it. And we also free the original array of strings, and then return null, and then memcpy chunks of I, and then text plus start, and then we have just basically here um, copying the text plus start. So text plus start is the starting index where we're copying, where we're starting to copy from, and the number of bytes will be length, right? So the number of bytes from this index text plus start, we're copying it to chunks of I. Okay, chunks of I length is you're skipping it. Okay, I mean delimiting it with /0 null termination. Yeah, that's what it's called. Okay, so and then count is actually num chunks, right? And then return chunks. Okay, that's cool. Yeah, okay, cool. All right, and chunk free is basically just taking all of this in, and we're actually freeing the each array element, and we're also freeing the parent array. Sorry, right? Okay, that's about it. Now we can go to go back to main.c actually. Now this is the whole chunk.h that we saw here, chunking parameters for the smoke test CLI. So chunk size, we're defining it as 1000, chunk overlap is 200 for this project, and type def struct constar. This is the model path, which is um, okay, this is the model path and the file path and the query, and this is the args that we're using so that we can call in main, right? argv, right? Okay, args, right? I'm using args though. Yeah, so that's what we're doing here. Cool, that's fine. So this is just a local struct for the args that the main function, I mean the main function takes in, the file takes in, and then usage. We're basically cast provoke, and then prog is actually, what is prog? Okay. Okay, this is the prog. Where's the prog? Okay, fine. Doc.txt, this is how you use it. So you pass in the model path using model flag, and pass in the file path using the file flag and query. Sorry. Okay, and the query is optional, right? Why is query optional though? Shouldn't it be compulsory? Minus k is int, so that's how you use it. So pass a tiny flags based CLI. We keep this expression no get out to stay pure C and readable. Okay, and then we're passing the args. So what are we doing is we're taking in the args structure and argc and a cap point argv, whichever. These are the global variables that main function takes in. So we're just passing it. We're just using this pass arg in main function, I presume, right? And then a model path is null. Okay, and we're just setting it to null first, right? Okay, we're just setting it to null, and k is 3 if it's not passed in, right? Why are you setting case to 3 though? One second. Okay, back. Okay, all right. Okay, my question is like, why are you setting k to 3 though here? I don't know actually, but this is what we're doing. This is what we're parsing it like. So if the string compare vfi and then model, right, for we're just iterating through argc from 1, 0 is the program, right, and argvi model, we're just comparing this, and if it is not equal and I plus 1 is less than argc, string compare is working like that, is it? So if string compare returns, I presume, right, 0, which means it is the same, and you're basically negating it. So if it should be 1 and I plus 1 is less than argc, right, uh, a model path is argv plus I. Okay, model path argv. Okay, 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 plus I again, query plus I, a to I, right, and then, okay, sorry, yeah, else if basically doing that, that's cool. Where, but the interesting part is like what we're doing is adding it first, incrementing it first, and then passing it down, right? Which is because the model should be 2. Okay, yeah, the next. Okay, cool. Yeah, correct. Yeah, this is correct because we have to increment it first, and then take in the model path, right? So after the flag, only the string of the model path comes in, right? And then this is the same. And I plus 1 is if it is there. So if this argument is there, so if I plus 1 again, the next, so use the flag. So for example, if I show you this, right? So model and then path.gt model, right? Uh, so I plus 1, this and I plus 1 is less than argc. What it checks is, it checks for the next argument, so if it is actually there or not. So we have to check for both of them, and then we just set it to all these things. And default is afk is 3, which is the default. You can just set it to here. So default k value set to 3. Alright, and then if a model path is not there or the file path is not there, return -1, right? So file path is actually the doc.txt. The file is actually the user query that we're doing, right? Okay, that's fine. And then okay, less than 0, return -1. That's good. Read a whole file into a single null delimited buffer. So this next function we have use size first and then a single read we return on a call say return buffer static card, and then we're just using static to internally link the function like that, so it's not externally linked. Read entire file, and then this is the path. So okay, that's fine. File pointer for fopen path rb. We're using fopen to open file in binary format though. So okay, that's basic error checking. Fseek, what this does, fseek takes in the file pointer after using fopen. 0 is the flag. I don't know what 0 means in fseek though. I've just seen it last week, but I don't remember. So let's see, man2 fseek, that's a man3. So fseek is long offset. Okay, offset. So this is the offset from secant. Okay, cool. So secant is the end of the file, and if it's not equal to 0, which means fclose of p and return null. Okay. Okay, so you're basically checking if the file is actually exists using fseek secant, and if the end of file is not existing, which means we just close it and return null, and then long n is equal to ftel of fp ftel. So which offset we are in. Now if n is less than 0, I've closed fp and return null again. Fseek of fp, we set it back to seek set, and if it's not equal to 0, which means again I've closed. So kbuff. So just checking this. So here fc yeah. So it sets the file pointer, right? So it sets the file pointer, right? So, and again fseek. What is the return though? Returns int. I know that, but you have successful if 0, otherwise -1 return like errors. Okay. So if it is successful, return 0, and if it's not, then yeah. Cool. Okay, fine. We're just checking if the file exists here. Start of the file exists, the file exists. Okay. Cool. Okay, and then kbuff is equal to basically malloking it. So we're just saving it to the buffer. So we have to free this buffer again if we want, if we care about it. Okay. And this one, okay, I freed. N is actually the length, right? ftel is okay. So I understand. So fseek is fseek to the end. N will be set to the length of the file. That's insane. It's a really good trick though. right? Element will be set to the length of the file in bytes, and then we can use n to set our buffer size, and then I've read buffer 1 size of t of n f p is not equal to size t of n f close of p f free buffer and return all. Okay. Okay. And setting back the right. Got it. So I've seek to the end, and then we're setting back here. Setting back the file pointer to the start of the file, so we can start playing it, right? And it's not equal to size n, which means it failed, right? What is actually f read though? Oh. Should be 2. No. F read is this size pointer and size the items. Reads n items objects each size. Okay. Okay, size of each block. Okay, that's cool. Okay, so we're just reading the size of the buffer. Sorry, we're just reading the size of one char of n blocks from the seek set fp and saving the buffer and saving to buff. Okay, that's cool. And then we're null terminating it, and if length, and then turn off again. Makes sense? Makes sense. So L2 normalized, which means they are normalized, which means they are divided by the normalized means they are divided by the magnitude, right? Magnitude of the vectors. Okay, and then we can just do dot product like this. Simple, clean and simple. Okay. And then print embedding preview. We will get a, what do we get using a model though? So here chunks, and then chunk of banks, qemb query, okay, query, and then ce scan chunk emb plus c2 dim. Okay, cool. So dim is actually the number of columns per vector, right? So number of vectors. Dim, n is the dims, which means is the number of vectors, right? Number of vectors in embedding. Number of vectors, number of unit vectors, or number of dimensions actually. Oh, that's why it's called dims. Okay, that's why it's called dims, bro. What the hell? Okay, okay, I understood. And then print embedding preview. Um, embedding chunk index dim and print. Okay, fine. Printing the embedding preview chunk index, and then that's too cool. That's fine. Brute force stop care retrieval against all chunk embeddings, and then which is basically dot product by k, retrieving k, right? Yeah, that's all right. Makes sense. Okay, this is takes the embeds context. Again, what is embed context if you ask me? That's the context of the model, right? I think, yeah. This is actually in embed.h. So if you do embed.h, load model path, right? Load is a, this is what embed.c is. So just after loading it, gives you the CTX context. It's kind of like um, all of these are GT specific, and GT already gives you all of these things, right? So GT load and GTT and the malloc of CTX and size CTX and then GT free and then makes sense, right? Malloc size, yeah, and then you're actually doing CTX GT is good GT, yeah, yeah, and that's the context actually. That's all. It's just a wrapper. That's all. It's just a wrapper around GTE. Fine, that's fine. Let's embed.h the load a GT model and get the context actually. That's fine. Free the embedding context, right? And then embed batch embedding embeds multiple texts. I think we're doing only a single text for now. Shouldn't we? We're also doing embed batch actually. We're doing embed batch if that's the case, right? So yeah, so we're also doing embed batch, is it? Yeah, we're doing embed batch itself, right? So the context and then the query and then the k and then chunk embeddings, number of chunks, number of dimensions of the embedding, and then cap pointer upon the chunks, the chunk actual chunks, right? And then okay, fine. Okay, query text is this. That's okay. And then basically what we're doing is float qm embed batch ectx q2 q text and then one embed batch, yeah. Embed batch really takes in the context of the model, embedding context, the q text, whatever q text the user query is, and then also one which is the dimension, is it? Let's see to show. Pretty calling GTML batch, fine. And GTML batch, I think it is a wrapper, so we can go to gt.c to do embed batch, right? And yeah, so it just basically calls GT embed. They count number of times, right? That's all it does. But if you want, you can go to GT embed. So this is the public API, and what it does is all of these things: L2 normalize and mean pooling, run transformer, tokenize, all of that stuff. But usually you just get the embedding, passing in the text, and just pass in the text in the context, and then the context you actually get it from get context, whatever, get context, CTX, right? Main model context, right? So this is the config, whatever the context, and this thing. I think there is function to get the context from the model path, right? I think so. Look up word in that layer normalization. All of these things are specific to the actual embeddings that we're doing, but not doing it. We're not doing all of that, but we need to actually. I need to actually do this learning. I think I'll ask Claude about all of this and how it's structured. Transformer forward pass. Then importing model loading. Exactly. So model loading is here. I think GT load, and then you get the context, right? That's what you're doing here. Check magic or whatever. Basically writing it to a binary file using Python, and then you're just reading it the same binary file, um, and then just filling into a struct. That's all. That's all. Right. So this is all that. So there's all that. Okay. So basically doing that embed batch and kk0k. That's cool. Best index is equal to calc of size k, size of int. Okay. I think okay. So alright, it's fine. I think I was worried about the lighting. So to find the best index, actually what we're doing is best score and best index. What we're doing is calcing size kk to size int. Okay. Okay. K is actually that. Right. Cool. So we're calculating it actually as an int pointer, so the array of ints. So array of ints, and each array filled with kk, right? stores many things, and then best index is equal to -1, best score is -2. Okay, I'm just doing that. Fine. And then dot product, and then for each k value, if the score is greater than best score, we're updating best score of s into best score of s -1, and then we're doing s -1. Okay. Then best score is score, and C, then break. Top percentage D matches, all it is top percentage D matches. Sorry, percentage top K matches, right? Printing it out and then freeing it. Printing it out and freeing it. Yeah, okay. So what is happening is read input documents. So we're just reading the entire file, put it into a text, and then chunk document into overlapping windows. Okay, so chunk text, we're converting into chunks. Load the embedding model, embed all chunks in single batch, and then embed batch, embed load, and then embed batch. Print a small preview so we can send it to check the embedding layout. So probably print out like something like, oh yeah, I already have it. So we can just do print. This is the embeddings. Oh, these are the embeddings for us. Embeddings. As follows. Printf, okay. Maybe we can do something like that, right? Sorry. Then okay. Let's go there. Residual mode, right? So embed the query in brute force the query, if the query is there or not. Actually, the query should be there, but anyway. And then clean up. Pretty much that's it, right? So file path. I'm just checking the file path is there. Okay, fine. Okay, so now I can do make clean, actually. Make clean. So we're just cleaning out all of these object files. Then making it, and then calling it like this. If you want to see, do you want to see doc.txt? This is doc.txt. This is the actual database that we have, right? Okay. So we're trying the top one. Sorry. So model is that, and embedding model is that, and then simple is that. So, oh, okay. Let me Let me change something. Oh, somewhere. Okay, fine. Let's check. Okay, here. I forgot this. Fine. Make clean again. Make. Okay. Oh, you want to see make clean again? Let's see make clean actually. I'm sorry, make. What it does is all of these C um, files, it's converting into object files, and then we're linking it with the LMNL curl, which is the math library, and what's the other library? I don't know. So I'm trying to make, we can do this. So the embeddings as follows. This is the embeddings, right? So we're not embedding the user query. We're just oh we should. Oh yeah. Yeah, we are. So the embeddings are follow the top two embeddings, right? So top one, and this is the top one match, right? That's cool. May not see. Want to see query. What's happening? Yeah, so embedding the query too, right? So we're doing this. That's cool. So now I think we can do generation part, right? So let's go to generation. Let's move forward. Let's move forward. Yeah, so I think we need to do generation for the version 1. Trying to build it from LNM.c, taking the retrieve chunks and setting them to tiny llama to generate an answer. Before touching, you do want to walk through what LNM needs to do. Yes. So this is the generation part we're using. We're trying to do the generation part again. So what happens is until now what did we do is like get a text right see text file a database, and then we're chunking into chunks using the embed.c. So we're just embedding it, and then we are store v1.c. We're saving it into a binary file embeddings using store v1.c, and then c will have all of these things and it'll generate an answer, right? So if you see store v1.h, what is this? So version 1 store, right? So flat binary file plus brute force scan. So on this format is this, right? So little endian amsterdam and the host, right? So u32 num chunks dim. So this is the header, the number of chunks and the dimensions of each embedding. Repeating num chunks types u and text length. Okay. Yep. So text length, text length, right? Hotel null terminator. Text of text length. Okay. why is it uint 8 though? We're writing it in binary, right? So each character is 8 bytes, so we're basically getting um, 8 integers of basically we're doing 8 number of ints. It's not 8 number of ints, so it's an integer of 8 bytes, right? So integer of 8 bytes and embedding, and then we're also saving. So essentially what we're saying, saving to the binary file is the number of chunks and the dimensions of each chunk of each embedding, sorry, and then repeated num chunks of type times, right? So uint32 text length, so text length, how much text is there for each chunk, and then text of text length, the actual text in uint 8, so integer of 8 bytes, and then because each character is 8 bytes, right? So and then float embedding of dim, so each dim is a float, and we're saving each uh, dimension, right? For 32. Actually, like, let's just make this clear for us. Make this clear. So I'll be back.